Hello. I'd like to go over a nice little example that I like to call the ice cube diet. And it's a good example to stir interest for students when you're dealing with heat changes, when you're heating up a body and a body might melt. And uh, so there's heat of fusion involved, there's specific heat involved. This is an example I often use in my classes. I call it the ice cube diet. How many calories of energy are required to raise the temperature of one glass of ice, which is 250 grams, let's say, from 0 degrees to body temperature, which let's say is 37 degrees Celsius? Now, you noticed I have capital calories. A nutritional calorie is a kilocalorie. But I'd like to work with joules, and then we'll make a conversion to calories. So the information we need to do this problem is the heat of fusion of ice, which is 333 joules per gram, and we'll symbolize that by L fusion, and the specific heat of water, and which is 4.18 joules per gram degrees Celsius. So for each gram of water, to change it by 1 degree, it requires 4.18 joules. And for each gram of water, of ice, to cause it to melt at its normal melting point, 0 degrees Celsius, you need 333 joules. Okay, this is sometimes called the latent heat of fusion because the heat goes in, but it doesn't change the temperature. It just causes the ice to melt. All right, so let's take a look here. So the heat needed, first we're going to have to melt the ice. It's the heat required to melt the ice. And then the additional heat needed to raise the temperature of the water from 0 degrees Celsius to 37 degrees Celsius. So the formula would be heat is equal to the mass times the mass of the ice times the latent heat of fusion. There's no temperature involved there, just causing solid water to ice, in other words, to become liquid water. And then for the heating up of the resulting water, we need the mass times the specific heat times the temperature change. So the mass is 250 grams of ice. It takes the 333 joules per gram of ice. So that's the heat needed to melt the ice. And then we have 250 grams of water, 4.184 joules for each gram degree Celsius change times 37. And so melting requires 8.33 times 10 to the fourth joules, and heating up of the resulting water is 3.87 times 10 to the fourth joules. So it takes a lot more, way more than twice as much heat to melt the ice than it does to heat up the remaining water, the resulting water. Add those two together and change it to kilojoules, and we get 122 kilojoules of heat needed. Of course, our body would supply that heat. Now, to change it to calories, and again, nutritional calories, 1.22 kilojoules, and there's 1 calorie with a capital C for 4.184 kilojoules, 29.2 calories. All right, not a great amount, but let's suppose you had 8 glasses. They say you should have 8 glasses of water a day. I never do, but let's suppose you should. If you take that, multiply by 8, you get 234 calories. I don't recommend chewing on ice all day. I don't think it's too good for your teeth, but it's an interesting problem. And in theory, it should require a fair amount of energy if you took all of the water you took in the form of ice. You could make it a little more interesting. Suppose the ice comes right out of the freezer and is 0 degrees Fahrenheit, which is the temperature of my freezer. So your ice is not at its normal melting point. It's 0 degrees Fahrenheit, which is minus 17.8 degrees Celsius. Interesting about this, the specific heat of water is 4.18 joules per gram degree Celsius, but the specific heat of ice is only about half as much, 2.11 joules per gram degree Celsius. Okay, so we're going to have to heat up that ice to its melting point. Let's see what the extra heat needed is. So we have 250 grams, 2.11 joules per gram degree Celsius, and the temperature change is 17.8, and that comes to 9.4 times 10 to the third. So the extra heat would be 8 times that number of joules divided by converting the joules to kilojoules and the kilojoules to calories comes to 18 additional calories. Not that much difference compared to the going from solid ice at 0 degrees to water at 37 degrees. Um, by the way, it's kind of interesting that the specific heat of water is much larger than that of ice. When water gets heated up, hydrogen bonds are broken, whereas they're maintained when you just heat up ice. They're largely maintained. I think that's a large reason why the water has a liquid water has such a large specific heat, and it's very important in our body, which is largely water, in our oceans. The specific heat kind of causes the temperature to remain fairly constant. It's difficult to change the temperature of a large amount of water because it has such a large specific heat. Okay, well, I hope you find that an interesting question to discuss with your students or to have your students pursue. It's always more interesting when you have an example that's kind of real or brings some interest. I think it motivates the students much more than just saying how much heat is required to melt so much ice and heat it up to a certain temperature. When you make it into a problem like this, I think it's more interesting. So I thank you for your attention, and I look forward to seeing you next time.